Okay. So, I think this one is actually set for ready to go. Yeah. Okay. So what we do is I'm going to start this plate. So what we have is our first wave has a slightly different frequency than our second wave. We're going to get that going. Ooh. Ah. So you can see what happens if we change this a little bit. Let's make this, let's see, I don't have it on my screen. Let's make this 10 instead of 1. Let's see what happens. So what are we doing here? We're changing the omega between them. Woo! Whee! All right, I don't want to give anyone a seizure. Okay, let's do the simulate though, because simulations are awesome, but there's nothing quite like seeing it for real. So what I have here are 2 tuning forks. This one has a little mass that's clamped to it. And so what that's going to do, what's that going to do to it? Yeah, it's gonna slow it down. It's going to increase its rotational inertia. So it's going to lower its frequency a little bit. So let me see if you can tell the difference between these two. I'll first ring this one. Okay, get that in your head. You guys hear it back there? Good. Okay, thank you for my choir. Let's do the second one. Can you guys hear the difference? Oh, of course, absolutely. My ear is very fine tuned. All right, let's do them at the same time. Okay, I'll do this one first. Sorry, that hurt your ears. Do you guys hear that? Wah, 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 wah. So what you're actually hearing here is you're hearing this amplitude go back and forth. Do you guys want to hear it again? Yeah, okay, let's do it again. So they are both oscillating at a different frequency that's off by maybe, I don't know. Well, we can figure it out. Oh my gosh. Okay, let's go back and let's talk about this. Let's see if we can figure out the difference between these real quick. Okay. So we know that this envelope is oscillating at a frequency delta omega over 2, right? So that means this has a period of T, let's call T envelope. Because this has to go up, down, and back up again. So that is equal to 2 pi over delta omega over 2. Ew.
That's 2 periods.
Oh, did I get 2? Okay. Okay, here's what I'm trying to say. My apologies. Okay, so what we want to say is that this envelope is going to oscillate with this period, right? With this period. Okay? So, how is this related to our omega? Yeah, Adam? Doesn't that start at the top and go to the bottom?
Yeah, no, no.
I hear a lot of chatter, sorry. That's half a period. But what do we hear? We hear it. So you're right. This is half a period of the cosine. What we hear is we hear the envelope, which this is a maximum and a maximum. You're right. It's only half the period of the cosine. But it's the period of what we hear is the amplitude going wah, 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 wah. So in reality, for us, it's going to be oscillating twice as fast as the envelope. So that means that the delta omega of the beats is equal to delta omega. All right? So, but we don't usually talk about angular frequency, we talk about sound. We usually talk about just regular old frequency. They're related by 2 pi. Remember that omega equals 2 pi times nu. So that means the frequency of our beats is equal to the difference in the frequencies of the 2 tuning forks. So now tell me if you could, we can guesstimate how close they are. Might be helpful if we count how many periods in a certain amount of time. Does anybody have a stopwatch on your fancy phones? On it? Okay. So what we're going to do, I want you to count 10 periods. Okay? Ready? What'd you get? You got 4 minutes and 20 seconds. Let's do it again. 4.28 seconds. Okay. Okay, so we got that 10 T is 4.28 seconds, right? Okay, so that means our T is 0.428 seconds. Let's see. That means our nu is 1 over T, which is 1 over 0.428 seconds. Somebody tell me what that is. Looks like it's around 2. That's my guess.
A bit better than this.
2.34. So that tells us that the difference between the frequency of these two tuning forks is 2 hertz.